Welcome back to this series of videos on enriched category theory. Last time we defined what a V-functor between two enriched categories is. We saw that such a V-functor, T, between enriched categories A and B consists of a map that maps the objects of A to objects of B, and for every pair of objects in A, we have a component map in the monoidal category V from the Hom object between A and B in A to the Hom object of the images of those objects in B. Moreover, these maps need to satisfy the following commutative diagrams. First, we want them to be compatible with composition, which is the diagram on the bottom left. And second, we want them to be compatible with the identities, which is the diagram on the bottom right. Finally, we also saw last time that this definition reduces to the usual definition for a functor when our base of enrichment is the category of sets. After this brief refresher of the definition, let's consider examples. Our 0th example is, as always, the case where our enriching category is set, and we saw that set functors are just normal functors. For our second example, recall that cat, the category of small categories, is a cat category. Thus, cat is enriched over itself, and if we have two objects in cat, so these would be categories C and D, then the Hom object that's between them is the functor category with functors from C to D. And this is a category where the morphisms are natural transformations. We now consider a cat-functor, T, going from cat to itself. And we want to see what the difference is between this enriched cat-functor when considering cat as an enriched category and a normal functor. We know from the previous definition that T consists of an object map which takes objects in cat to objects in cat. So this maps categories to categories. Second, for each pair of objects in cat, so these are categories C and D, which are objects in cat, we have a map, this is TCD, going from the functor category between C and D to the functor category between their images, so that's TC and TD. Now this map is a map in the enriching monoidal category, which in our case is cat. So in fact, this is a functor. So if we have some object in the functor category between C and D, which is just a functor from C to D, then this gets mapped under this functor TCD to a functor TF, which goes between TC and TD. So this specifies how this functor TCD acts on objects. However, we also need to specify how the functor acts on morphisms in the functor category. And such a morphism is a natural transformation, alpha, between a functor f and a functor g. So this has to be mapped to another natural transformation, which I'll call T alpha, going between Tf and Tg in the functor category TCTD. Finally, this mapping of natural transformations has to be functorial, which means that the image of the composite natural transformation between three functors has to be the composite of the image natural transformations, and that the identity natural transformation has to be mapped to the identity natural transformation. Therefore, the data of a cat-functor consists of an object map, and for each pair of objects, we have a functor between these functor categories. Finally, these object maps, which are functors, need to satisfy commutative diagrams that ensure compatibility with the composition and with the identities. If one writes out the commutative diagrams that we had in the definition, one can chase elements around those diagrams and get equations for what the functor needs to satisfy. If one has some element G in the functor category between categories D and E, and some element F in the functor category between C and D, then the compatibility with composition says that we need to have that T of G after F is equal to TG after TF. This is because the component of the enriched functor T maps F to TF and G to TG, and compatibility with the composition map. So the composition map in the case of cat is just composition of functors. Second, we also need the identity diagram to commute, and this merely states that if we take the identity functor on some category C, then this needs to be mapped to the identity functor on its image. So that's identity on TC. When we spell all this out, we see that a cat-functor actually has two levels of functoriality. On the one hand, it's functorial with respect to composition of functors, so that's horizontal composition of functors, which we could draw in the diagram as follows. So if we have a third category E, then we have the functor category DE, then our cat-functor is functorial with respect to composition of functors FG between these categories. So that's what's here in red. In addition, we have a second level of functoriality, which takes place within the functor categories, so within the Hom objects. So if we have some natural transformation between f and f prime, say alpha, then we also need this cat-functor to preserve composition of these natural transformations. We see that in the case of this example, the definition of a cat-functor compresses a lot of conditions into a very compact statement. For our third example, we let R and S be one object Ab categories. Recall that we saw in the video on examples of enriched categories that one object Ab categories are just rings. This is because they only have one Hom object, namely the one that goes between the single object and itself, and this is an abelian group, so we have the addition in the ring given by the abelian group structure on that Hom object, and then we also have a multiplication which is given by the composition map in the Ab category. So we'll denote the single Hom object between the one object and itself simply by R, and similarly we'll do the same thing for S. This will just make the notation easier. And now we let H going from R to S be an Ab-functor. What does this mean? Well, an Ab-functor needs to have an object map but in this case, the object map is trivial because we only have a single object in each category, so there's only one choice we can make there. Next, we also need component maps for every pair of objects, but this case is again very simple because we just have a component map H star star, which is a map between R star star and the Hom object of the image of star, which is star in S, so that's S star star. So this is just R with our notation from above, and this is just S. Now this map is a map in the monoidal category Ab, so in fact this is a group homomorphism. Next, because H is an ab-functor, we know that it satisfies the commutativity conditions from the definition. So these become the following diagrams. We can now chase elements around these commuting diagrams to see what the conditions turn into. So here we start on the left with an element A tensor B in R tensor R, and then we can either map that down to an element M of A tensor B, and then apply H to get H of M A tensor B. Alternatively, we could have taken the top path and mapped this to HA tensor HB, and then map that down to MHA tensor HB. And these two elements need to be equal. Now we recall that the multiplication in the ring R was given by saying that M of A tensor B is just A times B, and the same holds for multiplication in the ring S. Using this fact, we can reformulate what this equation down here is saying. This is just saying that HA times HB should be equal to H of A times B, where in the top case we're performing the multiplication in the ring S, and in the bottom case the multiplication is happening in R. Now recall again that the unit for multiplication in the ring R was given by the image of the element 1 under this identity map. So 1 in the integers was mapped to the multiplicative unit 1R, and similarly 1 in the integers is mapped to the multiplicative identity in the ring S. Now the fact that this right-hand diagram commutes is saying that if we map the multiplicative identity of R under H, then we should get the multiplicative identity of S. In summary, what a ab-functor is specifying is a single group homomorphism H between R and S, satisfying the additional conditions that H of A times H of B is equal to H of A times B, and that H of the unit, multiplicative unit in R, is equal to the multiplicative unit in S. So in fact, such an ab-functor is just a ring homomorphism. This is very nice because we have these one-object enriched categories which we can view as rings, and now the corresponding functors between them turn out to be the usual morphisms between rings, namely ring homomorphisms. Thus we again see that this general concept of an enriched category reduces to something we're familiar with in a special case. For our fourth example, we consider an ab-functor, which we'll call T, and this is going from a one-object ab category into the category of abelian groups considered as an ab category. So R is one object abcat, and this is the category of abelian groups enriched over itself. As a reminder, this is possible because the Hom set between any two abelian groups also has an abelian group structure. Now let's think about what T does. Well, T has some object map which will map the single object in R to some abelian group, which I'll call G. Second, we have a single component map going from R star star to the Hom object between G and itself in Ab, which is just its set of endomorphisms. To reiterate, this on the left is the abelian group underlying our ring R, and on the right we have the set of endomorphisms on the abelian group G, but considered as an abelian group. Now this component map, because it's a map in Ab, is a group homomorphism. And finally, we note that the endomorphisms of G have a ring structure with respect to composition. We can add maps because they're maps into an abelian group, and we can also compose maps sequentially just as function composition. Moreover, it's a consequence of the fact that these are group homomorphisms that the composition distributes over the addition. Another way of seeing this is by noticing that this Ab-GG is just a one-object Ab category, and we saw previously that this forms a ring with the composition being the multiplication in the ring. Based on our previous example, we also know what an Ab-functor between two one-object Ab categories is, namely it's a ring homomorphism. So in fact, we have a ring homomorphism going from R to the endomorphism ring on G, where the multiplication is given by composition. Let's spell out what this means. So our ring homomorphism takes some element of R to an endomorphism FR. Now, because it's a ring homomorphism, it means that FR plus S, so that's the endomorphism that R plus S is mapped to, is equal to FR plus FS, because we have plus being the addition in the endomorphism ring. Next, we have FR times S is equal to FR after FS, because composition is the multiplication in the endomorphism ring. And finally, we have that F of the identity in R is equal to the identity morphism, or just the identity function on the group G. Finally, we recall that these endomorphisms are group homomorphisms from G to itself, so if we have any elements xy in G, so xy in G implies that fr of x plus y is equal to fr of x plus fr of y. We've now done a bunch of translation and we're almost there. What we now have to notice in order to figure out what these conditions mean is that we can interpret an endomorphism fr as a scalar multiplication by R in the abelian group G. That is, interpret fr of some element x as r times x, where this is a scalar multiplication. And x is again an element of the group. And we'll also need a second element, so let's make it xy being elements in the group. Now if we write down the conditions again with this interpretation, we get that r times x plus y is equal to r times x plus r times y. Then we have that r plus s times x is equal to r times x plus s times x. Then we have that r times s of x is equal to r of s of x. And finally, we have that the identity in r times x is equal to the identity of x, which is just x. Now we see that these conditions are exactly what we need for a left R module. So in fact, an ab-functor from a single object ab category into the category of abelian groups, considered as an ab category, is just a left R module. To conclude, we'll consider the examples of Bool categories and cost categories. First, recall that a Bool category is enriched over the monoidal preorder false less than or equal to true with monoidal product, the logical operator and monoidal unit true. We now let P and Q be Bool categories. And we saw in the previous video that Bool categories are basically just preorders, where if we have the Hom object between any two elements being true, we interpret it as being like less than equal, and if it's false, then we have no relation between those objects. Now a Bool-functor, which we'll call F between P and Q, is an object map. So this just maps the objects of P to the objects of Q, together with component maps. And this is for any pair of objects in P. We have a map going from PAB to QFA FB. But maps between the Hom objects are maps in the monoidal category that we're enriching over, and in this case it's a preorder. So in fact, a map is just having that the left-hand side is less than or equal to the right-hand side. Therefore, a Bool-functor maps objects of P to object in Q in such a way that this condition holds. Now what does this mean? Well, if PAB is false, then this condition doesn't impose any restriction. However, if PAB is true, then necessarily QFA-FB has to be true. So if, let's say, if PAB is equal to true, this implies that Q, f of A, f of B has to be equal to true. And we recall that we interpreted PAB being true as A being less than or equal to B. And consequently on the other side, we have f of A being less than or equal to f of B. And so this condition is saying that if A is less than or equal to B in P, then we have f of A being less than or equal to f of B in Q, and this is just the condition for a monotone map between preorders. Therefore, again, we have that enriched category, in this case enrichment over Bool, gives us preorders, and the enriched functors, namely Bool-functors, give us monotone maps, which are the usual notion of a map between preorders. For our last example, we let C and D be cost categories, and we recall that a cost category is enriched over the monoidal preorder where we have the extended real numbers under the relation greater or equals than as the underlying category, with addition as the monoidal product and 0 as the monoidal unit. We now consider a cost functor, which I'll denote F going from C to D. So this is a map on objects, as always. And we have component maps FAB going from C AB to D FA FB. Similar to the previous case of the Bool categories, we're working with a preorder for our base of enrichment. So in fact, such a map is just a relation in the preorder, which in our case happens to be greater or equal than. Now we recall that we interpreted the Hom object in a cost category as a distance function. So we saw CAB as a distance between A and B. And similarly, we can interpret this the same way in the category D. So we get this being the distance between FA and FB. And now what this requirement is saying is that the distance between any 2 points should not increase under the map F. Therefore, in fact, such a cost functor, when we view cost categories as generalized extended metric spaces, is just a non-expanding map. So that's a map where the distances don't increase. This again continues our theme where we have some enriched category, which we can interpret as some known mathematical object, and then the functors, the enriched functors between those enriched categories turn out to be interesting notions of maps between the corresponding objects. This concludes what I wanted to say about enriched functors, and next time we'll complete the triad of fundamental definitions in category theory by looking at enriched natural transformations.